covered a little bit more completely. I've talked with one of my colleagues, and there's about 6 of us that are using Newton this semester for the first time in 1305. So if you kind of thought, oh boy, can I take 1305 any other way? There kind of wasn't another way this semester.
Is it going to be used next semester as well? For 1305?
I think so. I think we've headed down this path and hopefully, we'll fine-tune it. But I do know that students in other classes are, at this point in time are saying this is getting a little bit, this is a lot of effort. So that's why I've backed off on Module 10. I'm going to give a handout homework assignment, and I want you to know the concepts and the vocabulary, but I really want you to understand acids and bases, Module 11. So I will get you back on assignments there. All right, so what we're going to cover today, like I said, is dilution. Let's see what dilution looks like. All right, solutions and dilutions. And again here, M is molarity. Capital M, we're talking about molarity. So here's the practical situation you face. If you worked across the hall in the stock room and you're making up HCl solutions to go out into the lab, or you're in any other lab, and you want to make a hydrochloric acid solution, you are going to start with something that's 12 molar hydrochloric acid. This is concentrated hydrochloric acid. This is what we buy. We purchase a liter bottle of that, or 2-liter bottle of that. The analogy I like to use, I don't make orange juice this way, but maybe you do. It used to be very, very popular. People go in and buy a can of frozen orange juice, right? They take that can of frozen orange juice home to make their orange juice. They don't add orange juice to it. What do they add? Water. They add water. So that is a dilution situation. They're taking a concentrate and they're making a dilute solution, much more dilute. The concentrate is just this very concentrated orange juice with orange pulp and all that stuff in it. They let it defrost. They add water. So the orange juice they're drinking at home, when they pour that orange juice, every bit of the orange juice they bought from H-E-B. The only thing they added when they got home was water. Follow me? Well, just keep that in mind over here. So let's say this is 12 molar. This is our concentrated hydrochloric acid. And we want to make a dilute solution. Let's say we want to make it 6 molar hydrochloric acid. Over here, this is our dilution. So all we added to this beaker on the right is more water. We just added some water to it. So what does that mean? That the HCl in here equals the HCl that's in here. We did not add any HCl to the beaker on the right. You follow me? There is the same amount of HCl in both of those beakers. The amount of water does not equal the amount of water over here. As a matter of fact, basically what we did is we doubled the amount of water and it halved the amount of HCl. You follow me? That's what we did. We did a dilution. We took some quantity of concentrated HCl and we doubled its volume by adding that volume of water to it. Doubled its volume. And now the HCl that's in there is in twice the volume it was before. All right, so this comes up with an equation here. You got to. So if I'm saying the amount of HCl in there, well, how much HCl do I have in there? Well, I've got a certain molarity. That's a certain number of moles per liter. Let me look. Moles per liter. That's what molarity is. Times liters equals moles. Liters cross out. So this presents you with a very helpful little equation that molarity times volume in liters equals moles. If you ever want to, you're given a solution and you're saying, okay, I've got 50 milliliters of this and it's at this molarity, how many moles of stuff is in there? Well, molarity times volume in liters is moles. So, and what I'm saying, this little expression right here, let's get the water out of the way. That little expression right there is another way of saying that the moles of HCl that I have over here equals the moles of HCl that's in the dilution. There's the same amount of HCl in both of those beakers. So what are the moles of HCl in the first beaker? Well, it's the molarity of that concentrate times the volume of the concentrate equals the new molarity. The molarity of the dilution times the volume of the dilution. That's where that equation is coming from right there. That equation that you see on the slide, M1V1 equals M2V2, is flowing directly from this concept right here. That the amount of HCl in the original concentrated solution is equal to the amount of HCl in the dilution. Because all we're doing is adding water. All right, so let's see how we would use this equation. Yeah, here's the situation where you have, this is 12 molar hydrochloric acid. And this is kind of the assignment. You're in the lab, you're working in the lab, and you know that, or someone requests this solution. They want 500 milliliters of a 1.0 molar HCl solution. So that means in this equation right here, I've got to say, what is M1, what is V1, what is M2, what is V2. Make a 500 milliliter solution of 1 molar HCl using concentrated 12.0 molar hydrochloric acid. So this is M1. This is M2. This is V what? V1 or 2? 500 milliliters. V2. V2. That's the final volume of diluted hydrochloric acid we want. So this is, this is 500 milliliters. This is 1 molar. This is 12 molar. And you don't see it asking you right there, but basically this is what you have to find out. If I want to make that solution, I need to figure out how much concentrated HCl to start with. So M1 times V1 equals M2 times V2. V1 is our unknown, So I'm going to divide this side of the equation by M1. See, your solving of problems is getting easier because we've used the same method to solve all these problems. Isolate your unknown on one side of the equation. So then you put in your numbers. And if you want to stick with it. Now I said it needs to be in liters. I did say that. But we can leave this in milliliters, and our volume would end up in milliliters. Our V1 would end up in milliliters, and that's how much HCl we would get. Molarity crosses out. The V1 is going to be in milliliters. And what is that? So it's 500 divided by 12 is what?
41.67.
41.67 or maybe 41.7 milliliters of concentrated 12 molar HCl. So that there's our number. So what do we do with that number? You could well, okay, let's answer that question. Let's set this one up in the liters. We would have 1 molar. 500 milliliters is how many liters? 0.5. So if you did that, you would end up with an answer of 0.0417 liters. Is that right?
Yeah.
All right. And so what I'm saying, you can do this. You can do this problem with it in liters or milliliters. You just have to know what the unit is of your answer. Because I mean, we got 0.0417 liters, and if I wanted to convert that into milliliters, right? And why would I want to convert it into milliliters? Well, I'm going to go over into the lab and make this solution. So how am I going to make this solution? What's the final volume of this dilution? What's the total volume of the dilution? 500 milliliters. So I'm going to go get, I would go get a volumetric flask that is a 500 milliliter volumetric flask. I would go get a graduated cylinder, and in this case I would get a 50 milliliter graduated cylinder. And I would fill it up right here to 41.7 milliliters of concentrated hydrochloric acid. I would have rubber gloves on, goggles, and I'd be doing it in a hood. Because you open the bottle of concentrated hydrochloric acid, you know what comes out of there? HCl, fumes. And I mean, they knock you back. They clear your sinuses. I'll tell you that much. Not in a good way. All right, so you're in a hood, you got this HCl coming out of the bottle, you're pouring it into here. So then you would pour this in here, and you would fill it up with water. All right, here is your HCl. You're not going to add any more HCl to that flask, and you're going to add water to it. And you would end up with 500 milliliters of 1.0 molar HCl. Remember, this stuff right here is 12 molar. You're diluting it. That's how you'd make that solution. You follow me? All right, so Tasneem, to get back to it, in this using the dilution equation, Generally speaking, I think you can leave it either liters or milliliters. You just have to know how to report your answer. Okay, now all that said, I do want you to know that molarity, if you do want to know moles, if you want your answer to come out in moles, then you have to multiply by volume in liters. All right? Why? Because this is moles per liter times liters. Moles per liter times milliliters is nothing. Milliliters and liters don't cancel out. Follow me? So if you want your unit to come out in moles, you have to multiply by volume in liters. We were looking for a molarity, not moles, so we could play with it with either in liters or milliliters. But in this particular case, and I'll tell you where there are cases, I could give you, okay, this is dilution. Now let me give you another dilution problem and you do it. All right, do this problem. Now analyze the problem to find out what it is they want you to calculate. Figure out what is M1, what is M2, what is B1, what is B2. What's your unknown? What are they asking you to calculate? Okay, let's see. Calculate the molarity of a solution. So what is this? Here's our equation. We got 4 things in this equation, and these problems are going to give you 3 of them. So what is it asking you to calculate?
Molarity.
Which one?
Oh, the second one.
The second one, M2. Made by diluting 25 milliliters of 6 molar HCl with enough water to make 500 milliliters of solution. So this 500 milliliters is what? V1 or V2? V2. By diluting 25 milliliters of 6 molar HCl. So the 25 milliliters is what?
V1.
V1. And the 6 molar HCl is M1. All right, and you said, well, you told me concentrated HCl was 12 molar. Well, here is a situation where someone made 6 molar HCl and they actually want something that is lower molarity. They want to dilute it further, okay? So you can use whatever here. So now we know everything. M2 is our unknown, so we need to divide by M2. V2, no, we know V2. What am I doing here? No, I'm sorry. Back up.
V2 then?
We need M2. Okay. I'm going too fast. We need we need to get M2 by itself, right? That's better. That better? So M2 equals M1 over V1 divided by V2. And you put all that in, and what answer do you get? 0.3? Exactly? 0.3 molar. Great. Good. Okay, now there's another problem there. Let me take what we just learned, and one of the things we just learned is that molarity times volume. We learned that molarity times volume in liters equals moles in this context here. Let me go back and find a problem. Yeah, that's a problem. All right, let's look at this problem. This isn't a dilution problem. This is making a solution. We want to make 200 milliliters of a 0.125 molar NaCl solution. So this is a, how would you make question. How would you make this solution? All right? Just keep in mind, there are human beings walking around that know how to make these solutions. Where do they come from? They come from Northwest Vista College. Because someone taught them how to make these solutions. Okay? These things don't fall out of the sky. Human beings have to know how to do this stuff. That's why you're here. If you don't hear me, you're not a human being. Okay, so if you're hearing me, you fit into this category. So how would you make this solution? So we need 2 questions. We need to answer 2 questions here. The first question is, how many moles of NaCl is in this solution? Right? If you could answer that question, you could figure out how many grams. Is that right? Okay. So how many moles? Well, the moles are going to be, we're looking here now for moles of NaCl. So this equation, the molarity times the volume in liters, is going to answer that question. Follow me? You got the molarity. Now what's the volume in liters? 0.2. Remember, you move the decimal point over 3 places. This is point. And And what's the answer to that? And so then convert the moles NaCl to grams. Follow that? Luke, you with me? Okay. So we've got 0.025 moles of NaCl. We have figured this one out many times before. 58.44. So we add up 1 sodium, 1 chlorine, 58.44 grams of NaCl per mole. How many grams? One 1.46. And then finally, how would I make this solution? Well, I would need to get a 200 milliliter volumetric flask. I would add to this 1.46 grams of NaCl. And then I would fill it up with water. Let that NaCl dissolve in there, and I would have a 0.125 molar NaCl solution. Okay, you with me? So that's how you can use this equation. This is a really important equation. Whenever you see a question like this, it says how many grams of NaCl is required, or how many grams of NaCl is in this solution. Realize that the very first thing you have to do is figure out how many moles are there, and then convert the moles to grams. Because molarity is moles per liter. It's not grams per liter, it's moles per liter. Okay, now we won't take the time to do this problem right here. This will take some figuring, but you can see it. How many grams of glucose are present in 1.75 liters of a 0.500 molar solution of glucose? You're going to have to figure out the molar mass of this, and you'd use that equation. Molarity times volume in liters equals moles of glucose, and then go from moles of glucose to grams of glucose. All right. I just want to touch on the real highlights here. We got dilution. Now, oh, this really went ahead of me here. We will do a couple of these problems. Let's introduce it. So this is weight volume percent or mass volume percent. So some textbooks have this as weight volume percent. Let me write it a little bit smaller right next to this. Weight volume percent. Some of them use mass volume percent. Matter of fact, McGraw-Hill a couple years ago, their 7th edition had weight volume percent throughout all their problems and everything. They came out with the 8th edition and they shifted over to mass volume percent. I don't particularly like this because they're mass volume. It is they're the same thing, but you can see on mass volume you're starting to use the capital M for mass. When I'm telling you capital M, think molarity. Follow me? And so now they're using a capital M for two different things. Gets a little confusing. So you're going to just hear me say weight volume. I don't know what Newton does. I haven't looked into Newton to see what they do. Do they use W over V? Anybody seen it yet? Okay, well, let's just be aware that if you see mass volume percent, you're talking weight volume percent. Those are the same thing. And here's the definition. Grams of solute per milliliter of solution times 100%. Now you can see the weight volume percent is very different from molarity. Molarity, in the numerator you had moles. Here we have grams. In the denominator you had liters. Here we have milliliters. Okay? So don't get these two mixed up. Why is this used? This is what's used in clinics. This is what's used in the hospitals. When they say, I need a 0.9% saline solution, they're talking weight volume. I need 0.9 grams of saline per milliliter of solution. No, 0.009 grams. Yeah, okay, 0.9. Let's see if that's right. 0.009 grams of saline. Let's see if I'm right here. Per milliliter of solution times 100%. Okay? And that comes out to be a 0.9% weight volume percent saline solution, right? Am I right? Okay, so that's what saline is. It's got 0.009 grams of saline in every milliliter of solution. Saline solution. And when we get over to colliigative properties, you're going to, all of this stuff starts, you know, I'm teaching you these things one piece at a time, and then you get over here and you see that, oh, 4 pieces affect this. There are 4 of these things that come in to affect this. Why is this 0.9%? It's 0.9% because that's what your bloodstream is. It's 0.9% saline. There's 0.9% salt, ions, floating around in your bloodstream. And when nurses give you an IV, it has to be at this concentration. Any other concentration will stress your body. If it's too low or too high, it'll put a stress on your body. In other words, you can drink a bottle of water, but you cannot take a bottle of water intravenously. You say it's just water, but it's going to dilute your bloodstream in a harmful way. Okay, it's just water. It's pure water. I mean, I'm saying if it was actually purified water in an IV bag. They learned this in about the 1900s. I forget where it was when they first started doing intravenous things. They said, well, the person needs water. They're dehydrated. Well, give them water intravenously. And it caused stress. I mean, you could kill a person that way by just giving them pure water.
Same as you drink it if you overhydrate. You can still die. We gotta drink a lot of water. Do it. Like,
Right.
Put it to the main vein a lot quicker though.
Well, at least in the intestines, the body can make a decision as to what it wants to keep and doesn't want to keep and absorb. But once it goes into the bloodstream, it can't make that decision. So this is what saline is, and this is the way saline solutions are calculated. So I'm going to get that off of there because we got a problem right above here. So calculate the weight volume percent of 200 milliliters containing 20 grams of sodium chloride. All right, so remember, I've told you, start with your equation. All right? And then plug things into that equation. And so what percent solution is this?
10%.
It's a 10% solution. See if we got another one to do real quickly here. Okay, this is a harder problem. This is, how can I do this? Calculate. There we go. Let's do that. Calculate the number of grams of glucose in 750 milliliters of a 15% solution. I wish I had a slide here without the answer. I'd like to work out the answer before you see the answer. That's what I'm getting at here. So let's work it out right here. So we got weight volume percent equals grams per milliliter times 100%. Now notice that this problem is asking you to calculate this. This is your unknown. So you have kind of you have this situation. This is your unknown. And I've always said, before you start solving the problem, get your unknown somewhere. This is one where, I don't know, you might like putting all your numbers in here. Yeah, maybe you would like it that way better. So let's try that. So what we have, we got a 15%, 15.0% solution. We've got an unknown number of grams. Calculate the number of grams that's in this 750 milliliter solution. So if we kind of set this up the way I normally do, all right, like that. If I divide this by 100%, then I need to divide this by 100%. I'm trying to get this all by itself, right? And to get this out of here, I need to multiply by 750 milliliters, which means I need to multiply by 750 milliliters over here. All I'm doing is doing what I need to do to get X rod by itself. So I've got now X grams equals 750 milliliters times 15% divided by 100%. So calculate that. Everybody take out your calculators. Calculate that. Remember, you should be bringing the calculator you bring into your exams. What do you got? 112.5. Okay, I like that. She said she didn't know she got it right. 112.5 grams. Okay? Okay, now let me make a recommendation on this problem, because it is a little crazy and you can try to figure out, well, how do the units work out in this thing? Here's what you do. You know this. You know that equation, right? So now, take your answer. Pretend you don't know this. Okay? Take your answer and confirm. Put your answer here. Put your volume of your solution here. And what do you get? 15%. Is that what you should have gotten?
Yes.
That's what it says, okay? So I like that. You said, I got an answer here, but I'm not sure if it's the answer. Well, check it. Check the answer. Plug it back in and see if it gives you this percent. If it gives you that percent, it's the right answer. I do this. I do this on these problems. Because these get me all twisted around too on occasion. So I do this. I get my answer, I jump it right back in here. It takes 3 seconds. Punch it back in there and calculate it out and see if that's what you get. Okay? So that's about, I think that's about all we got to say about weight, volume, percent.
All the steps.
So there it is right there. There's the solution. It's moving it all around. And then check your answer. How? Weight, volume equals 112.5 divided by 750 times 100% equals 15%. All right? So check your answer. All right, so there's another one there. Like I said, there's extra problems. Sit down with a friend and work these problems out. Okay, we'll get to colliigative properties now. There are other ways of expressing concentrations. If you wanted to go to saws.org, I think it is, San Antonio Water System, and then look for water quality or something like that, and then look for their annual report. The annual report on San Antonio water quality. Why do I send you there? You will see every one of these units in there. Parts per million, parts per billion. So lead contamination is reported in parts per billion. Calcium or calcium carbonate concentrations in our water is reported in parts per million. It's about 130, 150 parts per million calcium carbonate. There's nothing wrong with it. Parts per 100 is a percent. That's what a percent is. Parts per 100. So when you get a 79% on a test or something like that, you've got 79 parts out of 100. That's parts per 100. There's even parts per trillion. The silicon grade that goes into computer chips is measuring boron, carbon, and what's the phosphorus, I think are the three. Boron, carbon, and phosphorus contamination at the parts per trillion level. It's almost I mean, it's a huge feat to even analyze for things down at those levels. But that's what messes with computer chips. Okay, water is a solvent, most abundant liquid on Earth. 60% of the human body is water. So we talk a lot about water solutions. It's a polar molecule. That's what gives it a high boiling point. Electrolytes in the body. Outside. So here we're looking at outside the cell. And that's inside. Inside the cell. This is really pretty fascinating. And maybe you've probably come across this in anatomy and physiology or some other courses you might be in or will be in. But the sodium ion concentration, potassium ion concentration differs. In the plasma, sodium is high, and in the cell, it's low. And in the plasma, potassium is low, and inside the cell, it's high. It's interesting. This is what the body's doing. The body is setting up a sodium-potassium gradient, concentration gradient, outside the cell versus inside the cell. So the cells of your body are actually determining, is transporting in sodium or in potassium and punching sodium out of the cell to make this gradient. And it is so active transport. So the body has to actively transport. The body isn't just relying on diffusion, because diffusion, these ions would just diffuse to come to an equilibrium and be at the same concentration everywhere. Okay, if sodium is too low, you start feeling thirsty, fever. It's too high, you can go into a stupor. And potassium is too high or too low, it can affect the heart in a very dramatic way. Other ions that are floating around in the blood, chloride ions. So the sodium and potassium are positive ions. There has to be a number of negative ions balancing them out. Chloride ions, bicarbonate ions. You can see if it stays there. You can see CO2 in here. CO2. That you gotta. So you can actually. So CO2 in water will form the bicarbonate ion. All right, let's get colliigative properties. What are colliigative properties? Properties of solutions that depend on concentration. They don't care what the solute is, just the concentration of solute particles. So colliigative properties don't care whether we're talking about sodium chloride or potassium chloride or sodium bicarbonate or whatever, just the number of particles floating around in the solution. And they affect certain properties, like boiling point. So we will talk about boiling point elevation, freezing point depression, and then osmotic pressure. And those are the three we'll talk about the most. Don't worry about that middle one, vapor pressure lowering. But these are the three I want to talk about. So what we are saying here, let's take water, and we know that water boils at a 100 degrees centigrade. There's its boiling point. Its freezing point, 0 degrees centigrade. This is pure water. Pure water, distilled water, nothing in it. What we're talking about here in colliigative properties is you put anything in water. Put sugar in water, put sodium chloride in water, just anything you dissolve in water will make the boiling point go up. That's boiling point elevation. So we're talking about boiling point elevation. It will make the freezing point go down. Freezing point depression. Now in your automobile you got a radiator. The radiator's it's filled up with antifreeze and water. Maybe about half antifreeze, half water. And the antifreeze is in there. It's in there to change the boiling point and the freezing point of the water that's in your cooling system in your car. Now you think you're in Texas. Why do I need antifreeze? I mean, when is my radiator ever going to freeze? But you know, you do need it to elevate the boiling point. The cars that are on the side of the road in August with their hood up and steam coming out from underneath it have just been topping up their radiator with water all the time. Just water, water, water. They've lost any antifreeze. They say, that's expensive. I'm going to just put water. Just put water in there. You just get water in there, and you got water that boils at 100 degrees centigrade, and it's going to boil over in August when it's 110 out, and you're driving, you know, in the middle of the day. It's going to boil over. Your radiator's going to boil over. Because what is the antifreeze doing? It's dissolving in water, and it's raising the boiling point of that water to 105, 110, 115 degrees centigrade. So now that it gets real hot in your engine, and the water isn't boiling yet. It's not gotten up to that pressure, and it's not going to blow the radiator cap. So you do need an antifreeze, even in hot climates. Boiling and freezing point depression. So up north when it snows, my wife was up in Minneapolis Friday. She was flying back Friday. It was snowing. She was getting out just in time. But they were, you know, putting ice on the roads to lower the freezing point of the water and depress the freezing point. Now there are equations that go along with this. You can look at some of these slides. What's going on? Why is this happening? Probably one thing you should appreciate is sodium chloride. If you put sodium chloride in water, for every 1 sodium chloride, you get 1 sodium and 1 chloride. So one of these gives you 2 particles. If you put sugar in water, one of these gives 1 of these. All right? It will depress the freezing point, but the same moles of sodium chloride will depress it twice as far as the same moles of sugar. Because remember, colliigative properties depend on particles. They do not care what the particles are. So a sodium ion has as much effect on the freezing point depression as a glucose molecule does. Those are each a particle. So, yeah, it's cheaper to put sodium chloride on the roads than sugar, right? And so keep aware of that ionic substances have a bigger effect on osmotic properties. So here's freezing point depression. You could actually, there is an equation. The number of degrees, so that delta T, the freezing point depression, is going to be, let's say delta T equaled 3. Well, the freezing point of water is 0. If the delta T were 3, it would say it now freezes at -3 degrees centigrade. It's saying, how far does it depress it? It depresses it 3 degrees from its normal freezing point. And you could calculate it here. Delta TF equals a freezing point depression constant. So every solvent would have a certain constant. Water would have a certain constant. Times a new concentration factor, molality. So all I want you to know is that you can calculate these freezing point depressions, boiling point elevations. There are equations for doing that. Does Newton go into this? Okay, these won't be on the test. The concept will be. What is a colliigative property? I expect you to know what we're talking about. What it does. So I got a slide here that says, so here's the one for boiling point elevation. Delta T boiling point elevation is another Boiling point elevation constant times the concentration of particles. Okay, let's answer this question. A salt dissolved in water will do what to the freezing point? A salt dissolved in water will do what to the boiling point? Increase. Okay, now let's get osmosis in here. Okay, this is an important concept for nursing and for the medical arena. Osmotic pressure. You get into anatomy and physiology, you get into physiology and what's going on in kidneys and in bloodstreams and in the intestines and different things like that. They're going to get into osmosis. What's going on there? Osmotic pressure. Now remember, this is a colliigative property. So it's a property that is affected by the concentration of things that are in the solution. Here's an example here of a cucumber. You put the cucumber down in vinegar and salt water and pickle it. What actually happens to it? It shrinks. It shrinks because here is high concentration of vinegar and salt out here. And what's inside the cucumber? Well, the inside the cucumber is not high concentration of salt. It's high concentration of water. You cut a cucumber open, you can get a lot of water. You squeeze that cucumber, there's a lot of water in there. But it's not salty water, it's just pretty much water. And what do you have on the outside? The skin of the cucumber is a semi-permeable membrane. It will allow water to transfer across that skin of the cucumber, but it won't allow the salt particles to go across. So we say it's semi-permeable. It is permeable, stuff will go across it, but only certain things, like water. So what happens? High concentration here of salt particles, low concentration there, and osmosis is a natural force playing out that is trying to equalize the concentrations inside the cucumber versus outside. All the cucumber can do with this semi-permeable membrane around it is diffuse water out of it. So this salt solution is actually sucking water out of the cucumber into the solution, and it's lowering the concentration of salt and vinegar out here. Does it ever get them equal? No. Never gets them equal, but it gets them closer to being equal. Follow me? It gets the concentrations moving in the same direction. It lowers this concentration, so there's a bigger, smaller difference between inside the cucumber and outside the cucumber. Okay, so what's cucumbers have to do with human bodies? All right, so here's what we're talking about right here. This is osmosis. So if I got a beaker and I took an adhesive and right through the middle of the beaker, can you please turn this light on? Thank you. Right through the middle of the beaker, I glued in a semi-permeable membrane, piece of saran wrap or something, or actually polyethylene maybe, right here, that allows water molecules. So the blue is water molecules. They can not freely, but they can pass through that membrane. But the salt can't. So I start out here, and what happens? Water diffuses over here, and this level goes up. And that is, if you think about a dam, the water behind the dam, there's pressure there. And the pressure is equal to the height of the dam. The dam gets higher and higher and higher. They need more and more concrete at the bottom of that dam. All right, because the pressure is going up, 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 up. So really, that difference in height is equal to a certain pressure. And that's our osmotic pressure. That's why we talk about osmotic pressure. It's going to push that up, you get more volume over here. You're losing water over here to dilute the stuff on this side of the membrane, and it creates osmotic pressure. Now, let me just show you the implications for the human body. So now we're not talking about pickles, we're talking about red blood cells. And so isotonic, here's isotonic. Let's start there. There's your red blood cell. What's inside there? Basically saline. And what's outside there? Saline. Equal concentrations. The concentration of stuff in the cell is equal to the concentration outside the cell. So water just freely passes. So as any water passes out, water passes in. Water, water. Through the cell membrane. But if you get to hypotonic solution, here's where yeah, so here's where if you put in an IV of just water and you diluted the plasma around here at a lower concentration, you're going to have water. You're going to have water flowing into the cell, and it's going to make the cell swell up and burst. Or the opposite thing, you could make it. You turn the red blood cells into raisins. They just crinkle up. All the water is being sucked out of the cell to dilute the salt that's out there because the salt concentration is too high. Okay? All right, I said I would give you this. I opened this one up. Joel, would you hand everybody one of these? This is let me just have one on. He's handing them out. This just goes by modules. And it goes by modules and just has some things, critical things in each of those modules. It has a little table here for writing out the formulas and some compounds. All right, this is your Module 10 homework. So it probably would help you, let's see, Thursday. This is Tuesday. It probably would help you Thursday to get started on this. I want to collect it Thursday.
We won't be here. We're live again tomorrow.
Thanksgiving. Okay. All right. Tuesday. We get familiar with these terms because we will go through this pretty quickly. This is your Module 10 homework. You're going to hand it in on paper. It'll be due probably next Thursday. But I'd like you to get familiar with this when we're talking about money. These are mostly definitions. If you look in LOH 06, usually it's in see, I'm not, I know. Okay, I'll turn it. Yeah. Usually anything they find out.
So I'm just
just tell me you want something.
see. Yeah. See my. Yeah, and that tells you when it is. I also
What did you do? Oh, you did the passport. Okay, I didn't do it off the passport. I did it off of whether you labeled bottles or worked at our table. Where did I track that? Okay, I was mostly doing, did you think if you did the passport, you did? Did you? Yeah, see, here's everybody labeled bottles. This is where I put the extra credit. Did people label bottles, or did they show up at the table? You see your signature in there? Okay, well, what is your name? Spell it. Alright, what did I do? 50 points, right? Looking for the black book. Put it down here.
It should be on. Oh yeah, the resources there. It's probably over harder. That's what
Okay. I'll give you credit for it. So I'll put in 50 points. Alright? Okay.
you can't bring a receipt when you're
Alright, see you.
don't add you have to put something from the person what you wrote in there. Yeah. But faces that for your reasons, yeah. Now this is yours.